Hey there, welcome to the presentation on my data science project titled Informing the Zestimate, where I will be exploring any patterns or relationships between access to outdoor recreation and the sales price of real estate. A little bit about me before we get into the project itself. My name's Taylor. I'm currently pursuing a master's degree through CU Boulder, and this project is for my class titled Unsupervised Algorithms in Machine Learning. So you might be familiar with tools such as Zillow's Zestimate, which provide predicted sales prices of real estate. These tools are known as automated valuation models. And while these models are very sophisticated and proprietary, I don't believe in my research that I found that they take into account uh, access to outdoor recreation in the way that I am proposing. Again, the goal of this project is to use unsupervised learning to explore the potential of integrating outdoor recreation into automated valuation models for real estate. And the two sort of features that I'll be looking at in measuring access to outdoor recreation are trailhead proximity and activity density. And we'll get into what exactly I mean by that. The machine learning tools I used in this analysis include k-means and hierarchical clustering. And basically what clustering is algorithms that help you group observations within your data set together to sort of explore and see if there's any underlying patterns in the data that could give you any interesting insights. I was able to generate my own data set for this project. I live in Auburn, California, in the United States, where we have quite a bit of outdoor recreation going on. We have a lot of trail running and a lot of trailheads and close to town. And we also have a lot of folks that mountain bike and cycle on the road. So I was really interested in looking at my hometown for this exercise. And I was able to scrape about 4 years worth of residential real estate sales data off of Zillow, which gave me about 1,300 observations in total. And for uh, generating data having to do with trailheads and activity density, I went ahead and mapped 36 trailheads myself. And what I mean by trailhead is a general access point that folks might use to access these trails. Some of them are official with signage, and some of them are trails, let's say, that might cross a road. And I just know from personal experience that uh, people might access trails there as opposed to the official trailheads. And for activity density or activity data, I was able to download my personal data from an application called Strava. You might be familiar with it, where it gave me all the GPS pings for all my activities that I've recorded. After I scraped the data from Zillow, I did a little bit of pre-processing where I selected the features I wanted to use. These included the number of bedrooms and bathrooms for each observation, as well as latitude, longitude, the sales price, and the lot area. 19 of the observations had missing values, so I just decided to get rid of them. And then finally, I did a little bit of unit conversion on some of the observations just to make sure all the units were matching. I also did a little bit of outlier removal using interquartile range, and you can see the equations I used here. So in order to integrate uh, this trailhead proximity idea into the data set, I came up with a metric that I call trailhead score, which basically represents the distance that a certain property may be from trailheads. And the trailhead score is meant to represent access to trails, including running and mountain biking trails. And you can see all those trailheads that I mapped here in this image. And again, this was based on personal knowledge that includes official trailheads and just points of access that I know through experience. And this introduces a lot of bias because I'm the only one choosing these. This is not a public data set. There's no real rules agreed upon on how I chose these. So just keep that in mind. The trailhead score for each property is calculated as the average distance of the five nearest trailheads from that property. And then I took the inverse of this number just to make it so that larger trailhead scores would be associated with closer proximity to trailheads. And the distance that you saw in the previous equation was calculated using latitude and longitude information in the Haversine formula. And before I got into the unsupervised learning aspect of this project, I thought it'd be interesting to run a multiple linear regression, including all my features with sales price as the response. And what I found is that we have an R squared of about 0.5, and that all of the predictors in the data set were found to be significant. So nothing mind-blowing here, and the point of this project isn't to make predictions, only to explore the data for any underlying patterns. But I thought this was interesting nonetheless. So for the unsupervised portion of this analysis, I chose to use clustering. So what is clustering? Clustering techniques are a set of machine learning algorithms that one can apply to their data with the objective of grouping the data into clusters. And those clusters may or may not provide insight into underlying patterns in the data. You can see here a image I generated in Python where we have 3 clusters. And these clusters are pretty uniquely defined. There's pretty good separation, but sometimes there's more overlap. And you can imagine, let's say for this analysis, the x-axis could be price, the y-axis could be the lot area, and z-axis could be trailhead score. And maybe we could see some interesting relationships within the subsets of the data. I mentioned that I employed k-means and hierarchical clustering, and for this project, I was looking at the difference between the two. Just a little blurb about what they are and the differences. K-means randomly selects a certain amount of centroids, which would be the center of each cluster. Those centroids are assigned the nearest data points to make up the cluster. And then as we iterate through this, the centroids are recalculated based on the new points added to the cluster. And that process stops once the centroid positions stabilize. Hierarchical clustering, and in this case, I use agglomerative clustering, which is a bottom-up approach. Each data point itself starts as a cluster. And then with each iteration, the 2 nearest clusters merge, forming a new cluster. And this continues until all of your data is included into one cluster. And then somewhere along the way, you make a determination of how many clusters you want to include in your analysis. So a question you may be asking is, how many clusters do we need, or what is appropriate? Some of that might depend on your domain knowledge for your specific problem. And you can also use metrics like silhouette score, which is what I used in this analysis. And the silhouette score is basically a measurement of that separation. How much overlap do we have versus how well are the clusters defined without overlap. For both hierarchical and k-means clustering, I found the optimal number of clusters to be 4. Typically, you would want a silhouette score higher than 0.3, but this is what we have with the data we were given in this case. Here are some of the results from k-means clustering on the data. There's a lot of features here, so it's kind of hard to illustrate the clustering in just one figure. But here's a pair plot showing the different features plotted against one another. And by the way, I did all this analysis in Python. And so maybe we can see some interesting things here. Cluster 1 seems to show sales with higher prices and higher proximity to trails, whereas clusters 3 and 4 don't really seem to be affected by their proximity to trail access. And then one other interesting thing of note that I thought was cluster 3 is associated with properties with higher lot sizes, and their prices range from low to high, and they seem to have they seem to not be affected by their proximity to trails either. So, these subsets perhaps show the decision-making going into people's purchases of their properties. And especially in cluster 3, it appears that maybe in more rural settings where people are buying acreage, that proximity to trailheads just isn't an important factor. Here is the same pair plot visualization for hierarchical clustering on the data. And we can see that the results are very, very similar. You have the three main clusters where uh, price doesn't appear visually to be affecting two of them, whereas the third perhaps may be affected by its proximity to trailheads. Now, because I was mostly interested in the effects of trailhead proximity on sales price, I decided to go a little further and do some segmented linear regression on the different clusters. Nothing too crazy to see here, but definitely we can see there is a little bit of linear relationship between trailhead score and sales price in cluster 3 and 4. Here are the numbers behind those linear regression models. Again, nothing too earth-shattering here, only 0.16 about for our R squared values. But it is important to note that linear regression isn't the only way of using a feature to model an outcome. So I think that in future exercises, you could utilize something like supervised learning with a feature like trailhead score. And so, yeah, another thing to note here is that for the Shapiro-Wilk test, which tests the assumption that your residuals are normally distributed, and then you can therefore apply linear regression, I relaxed that p-value to 0.01. It's usually 0.05. So not very strong indication that there is a strong linear relationship between price and trailhead score, but I do think there is a little something here. Here is a mapping of those clusters, and you'll notice that cluster 4 is pretty close in proximity to all those red dots on the map, which represent the different trailheads. And so what this might be telling us is that these neighborhoods may indeed be affected in terms of trailhead proximity and sales price, while other neighborhoods uh, simply may not be. The other neighborhoods, people might not even be looking for that as an amenity. The next step in my project was to apply these same methods to recreation density. Now, to feature engineer this into the equation, like I said, I downloaded my personal data in the form of GPX and fit files from Strava. And these files include my activities on the trail and the road for cycling and running. And the GPS pings within those files were used to generate the heat map that you see here, all using the GeoPandas library in Python. And these values within each grid cell in the heat map were used to feature engineer something I was calling the recreation score. I calculated the recreation score as the density of GPS pings within a certain uh, cell of the heat map and over the distance from radius D that that cell had from a certain property. There are a few parameters I played with in calculating this recreation uh, score or recreation density feature. One of those was the cell size within the heat map. While it would be nice to use a very granular level of detail that comes along with the necessity for a lot of compute power and a lot of time in order to do calculations using each one of those individual cells. And I thought it was actually appropriate to use a larger radius. So let's say in this case, I used 10 kilometers from each property. And therefore, I was able to use a larger grid cell size, just aggregating those points into fewer cells. So I had to do fewer calculations to calculate the recreation score for each property. Um, Again, this comes with a lot of potential bias, right? Because this is my own personal heat map. And even though there's a lot of data here, uh, it's really a sample size of one, right? So I decided I needed to uh, have a buffer zone and also remove outliers from the data because a lot of my activities start and end at my place of residence. The heat map is very, very dense around my house. So I thought I needed to, remove those observations, if any, from uh, the data set. Now, there's really a limit to this, right? Because I had to select either a time frame for my activities, start from the start and the end that I would sort of chop off so I could not be overly impacting property sales and to rec score close to my house, or I could use a spatial sort of buffer zone. I use the spatial zone, but this is limited because even though I use this buffer zone, the points immediately around that buffer zone would always be uh, biased towards the activities starting and ending at my house. Here are the results of the clustering using recreation score and hierarchical clustering. Both k-means and hierarchical gave very similar results, but you can see that these results are actually similar as well to when we were using trailhead score. Cluster one has above average prices and low proximity to recreation. Cluster two, below average prices and low proximity to recreation. There's this cluster three, which has uh, higher proximity to recreation, but in this case, we can't tell really visually if there's an effect on the price within those neighborhoods or this cluster of properties. And then cluster four, where there's a range of prices and they seem to be associated with properties with larger lot sizes. So there's a lot going on here. There's probably even more underlying patterns. Uh, you might expect to see a more linear relationship between features like the number of bedrooms and price or lot area and price, but this is what we have at this point. So, in conclusion, I do believe there are potential benefits for incorporating outdoor recreation metrics like trailhead score or this recreation score into automated valuation models. Um, and it's pretty obvious that linear regression may not be the optimal method for actually measuring their impact, but I think supervised learning might provide even more insights. So that being said, future work in this space could include expanding the real estate data set beyond just my hometown and using a global set of trailheads or a more global heat map data so the bias is mitigated. And again, like I said, maybe we could use supervised learning to actually measure the impact of utilizing these features. And but I think this exercise did or does display a potential uh, for integrating outdoor recreation features into valuation models. You can find my code and the data sets available on Kaggle at the URL below. And I thank you for listening to my presentation. See ya.